In the previous video, we talked about costs, and especially in the short run, when we are using only one variable and the other is fixed, we usually fixed capital, and we said we can find, say, the change in cost or marginal cost as wage times the change in labor. Just additional costs when we hire more labor in order to produce more stuff. Looking back at the big picture in chapter 6, we had talked about production functions and isoquants. If you know your production function, you can map out all of the combinations of labor and capital that will result in some specific level of production. And now we are introducing a cost constraint or isocost line. So sort of just like before, we have some overall total cost, which is equal to how much we pay for labor, the price of labor times labor, plus the price of capital times capital. We tend to think of the wage rate as being set by the market in our examples. And then there's a little section above here on how we derive the rental rate of capital. I'm going to mostly leave that as a discussion for 304. So the main takeaway from this section on 7.3 cost in the long run is really just ultimately that in the long run, we're going to use both labor and capital. We might vary our labor and capital in the long run, and each of those inputs has a price. The price of labor is a wage rate W. The price of capital is the rental rate R. Right, just like before, we could graph this out. The endpoints of this isocost line are going to show us, all right, if we only hire labor, given some total cost constraint, how many laborers or workers could we hire? Or likewise, if we only hire capital, how many capital could we hire on a given cost? Those are going to be the endpoints of our isocost line. And just like before with the budget line, we can ultimately see that the slope is going to be negative W over R, or the price ratio. Remember, as we come down here, we tend to be graphing labor on the x-axis and capital on the y-axis. So the price of labor is W, the price of capital is R. We have, again, essentially a negative PX over PY. Right, so this slope of our isocost line is a very similar idea to the slope of the budget line. Again, if we look at any particular isocost line, so we have three different isocosts here, C0, C1, and C2, which are representing, here's the lowest cost and here's the highest. Right, let's look at this one. K2 represents the point right here where we hire zero labor. We spend all of our cost or all of our budget on capital, and we hire this many capital. All right, same thing down here for labor. So just like the slope of the budget constraint was ultimately negative PX over PY, in this case, we have negative price of labor over price of capital, or negative W over R. So suppose that the producer wants to produce some certain quantity level, we call this Q1, and wants to know what is the cheapest or optimal way to produce Q1. How would we find this? Well, once again, we're going to have this tangency condition. Why? Well, again, all of this points on Q1 are possible capital and labor combinations which result in the production of this quantity Q1. And we can see that point A here, the tangency point, is on this isocost C1. What about if we wanted to produce Q1 in some other way, right? We could produce Q1 using any combination out here. We could produce Q1 using any combination out here. Would any of those be more efficient than A? No, because we can see there's this whole field of isocost lines. Like for instance, if we use this point right here, that's on a higher cost line. So we can see that the producer could produce the same quantity Q1 at a cost of only C1. So a point like this would not be optimal. Right, likewise over here, producer could produce Q1 using this combination, but that also costs more than A. Right, so the cost minimization problem that we're looking at for the producer is very similar again to the utility max problem that we looked at before, but in this case, we have some sort of set quantity that we want to get to, and we're trying to figure out what is the lowest cost possible to produce that quantity. The result is once again a tangency condition, and so mathematically we can find that tangency condition. We know that the slope of the isocost line from the previous video is change in capital over change in labor, which we can prove mathematically is MPL over MPK. It will always be MPL over MPK, so try to commit that to memory. MPL over MPK, so the slope of our isoquant here, slope of Q1 is MPL over MPK. And then the slope of the budget line, of any budget line, is negative W over R. So ultimately we have MPL over MPK equals W over R. Right, so here is our tangency condition for a producer cost minimizing optimum. In the next video, we will talk about specific mathematical examples. I'll go into the example problems for this week, and we'll actually solve that out in a very similar way like we did in chapter 3 up until the very last step, the plugging in step. Right, so that's going to be most of the things for this chapter. We can see an expansion path, one more important definition here, is going to show us as we want to increase our quantity. So here we show 100, 200, and 300 unit isoquants. Right, so suppose the firm starts out producing at point A, which is 100 units, and the firm says, we want to increase our quantity to 200 units. Right, well, we can see that B is now the optimum point, most efficient, most cost efficient point. What if the firm wanted to instead produce 300 units? The optimum point is C. So the expansion path shows us as the firm expands its quantity, what are the cost minimizing points, right? And then we can ultimately graph out this long run total cost curve, which just shows us for any given output, what was the most efficient or optimal cost. So we can see that here, when we wanted to produce a quantity of 100, the optimal cost was on this 1000 isocost line. I guess that one's not labeled, only these two are, but we can infer that this would be an isocost of 1000 from here. When we wanted to produce a quantity of 200, we're on the 200 unit isoquant. Our most efficient point was on this 2000 isocost line. So the efficient cost is 2000 to produce 200. And if we're on this 300 unit isoquant trying to produce 300 units, the most efficient point is C, which is on the $3,000 cost line. So that's our long run total cost. Right, so an expansion path is kind of similar then a little bit to some of the things we did at the beginning of chapter 4, just talking about if we want to change our total quantity, what is the most efficient way to do it? We can map out our optimal points. All right, so I'm not going to do much, really anything mathematically with things 7.4 and beyond. There's a couple just quick definitions. Economy of scale versus economy of scope that I'll just post the definition to, and there might be some sort of definition question, but we're not going to deal with the equations and stuff here at the end of the chapter. I really want to focus in on being able to find these optimal bundles, going back and being able to do it for the consumer, and then in this chapter being able to find optimal bundles using this rule for the producer. All right, let me know if you have any questions.